Hey everyone. So the first question I have here with the first slide here is, what is sentiment? So sentiment is the underlying emotion or meaning behind something. So a sentiment could be anger, happiness, or in general you could make it positive or a negative sentiment. Here's an example of some sentiment. Not really useful if we take it out of context. If we didn't know The Wolf of Wall Street and we didn't see this one-star review, we'd be like, what does this even mean? There were no wolves in the movie. Useful, thank you. But once we add one, we can see, oh, it has a 1 out of 5 sentiment, so we can assume probably pretty negative. But this is just one example. So I'm gonna take a quick little second to introduce myself and where I'm coming from. I am Derek. My last name is Wa. Don't be deceived by the way it's spelled up there. It is French. I am in computing science at SFU. Doing my undergrad in my last year. I have been interested in data science for a while now. I got interested first with big data concepts in hospitals. So I heard about them using the instruments in hospitals and collecting the data from it. That way they could understand when someone's about to crash and prepare for that kind of event. That made me very interested in it, and only recently I started researching more into big data. Over the summer I took a computational data analysis course at SFU. Where I learned basics in Python and some of the libraries in there. Currently, I am trying to broaden that basic understanding that I got, and I'm studying Python, R, statistical modeling, and hopefully in the future I'll be moving into more Keras and deep learning as well as machine learning concepts. I will be talking about that in here, so as a brief note, if you guys do feel that I'm saying something wrong or you feel that you want to talk about a topic a little bit more, don't be afraid to discuss it with me. Any input is great. I'll be doing an overview talk on most of the concepts, so it won't be very in-depth comprehensive. So if you want to have that kind of discussion, please take charge of that and talk about it. I have 2 brief plugs I'll be putting in here. I am looking for co-op. Please hire me. I need I need to use my experience that I've gained from all my years at SFU before I graduate. I recently, over the weekend, was in a Halloween hackathon competition. We were doing environmental applications where we'd try to build a business that would educate as well as help the environment. We ended up winning that competition with me and my team. So I'm looking for anything, QA to software development, honestly just trying to apply what I've learned. I'm very self-learning. I'm self-learning myself in data science as well as full stack development. So about the plug, if you are interested in talking to me about job postings or just connecting, I'd love to talk about anything. Computer science topics, data science, just hit me up on LinkedIn. There's the link. You can find the slides. Second plug, this is my dad. You can see by the name. He's been working at IBM for 20 years, and he is in the data streaming analytics department. He has recently started a YouTube channel called Bite Size Data Science. Right now, he's got about 5 videos up, and they're all kind of like intros to data science. So if you're new to data science and you want to learn a little bit more or get a brief understanding, check it out, see if you can follow it. It'll probably give you at least some background knowledge. Anyways, now that self-promotion is over, I'll move on to the competition that I looked at. So this competition, our goal was to predict the sentiment inside of movie reviews. We took a corpus from the Rotten Tomatoes database. So Rotten Tomatoes is where users get to rate a movie and they will say, oh, okay, this was good, this was bad, and it gets an overall rating from that. What happened was, it was Pang and Lee took that data set and used Mechanical Turk through Amazon in order to get people to rate sentiment for phrases inside of these reviews. So these phrases were anywhere from negative, somewhat negative, neutral, somewhat positive, to positive. I have it listed from 1 to 5 here, but in the data set, it's categorically represented as 0 to 4. So after getting this, they created a sentiment tree. So the goal in this competition was actually to take this review sentiment, train it in some model, and then be able to predict some random set and figure out the sentiment for it. So this posed a few interesting issues. So there are things like sentence negation. So when we have a sentence that's negated by the beginning, so I could say, no way in hell, or like hell before something. So like hell, I'd go to that again. All of a sudden, I'd go to that again, which would be positive, becomes a negative sentiment. we have to watch out for sarcasm. So I could say, oh, this movie really takes you places. First I was in the theater, and then I was asking for a refund. That's an example of some sarcasm. I don't think it would be picked up very well by any kind of machine learning algorithm. Next one is terseness. When things are very short and brief, so you could be like, movie's aight, very colloquial, but you don't really get much information from it. Then we move on to language ambiguity. So this is when a phrase can be understood in different ways. I could say, again, colloquially, that movie was sick. Or I could say, that movie was sick. Very different feelings. One's disgust, one's like, oh, that was amazing. So there's a lot of nuances to language, and it makes it very difficult to understand or classify. And we'll have to think about that and face that as we're going through this problem. Yes?
Did you see the sentences like this in the data set where they're like...
Not really, but if you, later on in this slide, we'll look at some of the words, and you can kind of see, I'll try to point them out, but there is some little bit of like, you could almost see like colloquial stuff in the words that do show up in this data set. So moving on to the leaderboards. Most of the leaderboard was about 69 to 71% accuracy. The top one was 99% accuracy. I have no idea how they did that. I looked at the kernels. I couldn't find anything better than like 69, maybe a 70% accuracy rate. So as far as I know, it's magic. But when we're looking through our solutions, keep that in mind. The solutions that we have are about the lower end of the top 10 or maybe in the top 20.
I have a comment on that. They were almost definitely cheating, those guys.
Yeah, no, I wanted to say that, but like, I didn't want to insinuate anything, but like 99% is ridiculous.
I think this is I don't know if anybody is familiar, but I think this is like a publicly known data set that they may have been able to look up.
Yeah, it was. They probably just inputted the actual testing data set in, and like then they already had the answer.
Yeah.
So, because I looked at that, I'm like, that's 28% higher than the next leading score. So they're clearly cheating or doing something that no one else had access to. So with that said, we're moving on to the data. So the data is divided into a few sections. I will start with the second column, so sentence ID. I like to look at it like this. There's the sentence ID, and then you have that as the parent, and then there's the phrase IDs under it. So a sentence can contain many different phrase IDs. The next section is the actual phrase. So this is a phrase that's linked with our phrase ID, and we can see that there's a few repetitions. Like if we look at a series of escapades, it goes down again, and then like the third one down in this row, sorry, I'll point this out. The third one down in this row is just a series. So there's a lot of repetition, and it gets very granular. After phrase, we have our actual sentiment. So this is ranked from 0 to 4. We see a lot of 2s. We'll go over that in a little bit. There are quite a bit of 2s in this. So a very neutral sentiment. This is the testing data set. Since it's a competition, we completely leave out the sentiment. And a lot of the solutions that we will look at, they chose to do about a 20% split for their validation set so they could actually test the accuracy. So this will be what we're looking at when we're looking at accuracy for some of the later solutions. This is a sample of the output. We're going to do a phrase ID, and we're going to hook it up with a sentiment, and then that should be the output, and that will be what we test accuracy with. So here's a graph I made with Python. We have our positive, somewhat positive, neutral, somewhat negative, and negative sentiment. If you look up here, sorry, this is like a little bit hard. Positive is at 9,000, and the opposite, negative, is at 7,000. So there's about 2,000 difference. It's a little bit leaning towards positive. We have this excessive skew of neutrality, where it's about 80,000 neutral phrases. Continuing on, this graph, I squashed down the phrases and just went by sentence ID. So we're looking at the overall sentence ID sentiment, and we see that we lose a lot of neutrality, and we definitely lose a lot of data. It ends up going from being hundreds of thousands of phrases to probably 7,000. But it does preserve at least the skew a little bit. There's a few more positive than negatives.
There's a question in the middle of it. Yeah.
Hi, sorry, I didn't understand the sentence ID thing. Is that because there are some repeated sentences? So those are the unique ones?
Okay, sorry. The back here, what I illustrated here was that see how there's a repetition of twos, and it's basically the same sentence. So we see phrases getting repeated over and over, and they might not have much variance. We'll have a lot of the same sentiment for certain phrases inside of a sentence. So when we squash those together, we all of a sudden went from having 50 occurrences of a neutral if the whole sentence was considered neutral to like 1. Does that make a little bit more sense?
Yeah. What's the source of that repetition?
What?
What is the source of that repetition? Like those sentences are repeated?
No, these are phrases. So like I said earlier, the phrases are pieces of the sentence. So the overall sentence might be like a neutral sentence, but then we're breaking it down into each phrase inside of the sentence. So right here, we see it's a series of escapades. Just can't read from this angle, but do what?
Series of escapades demonstrating.
Series of escapades demonstrating, and then we go down a few times. So this is almost a repetition with just a few words taken out, and then we go down to just a series, but we still remain with that same sentiment. So by squashing all these phrases into the sentence ID, we lose a lot of repetition. And I thought it would be a good way to show you that fact, and we will be talking about it a little bit later and showing why that might be happening.
Okay.
All right, so this one moves on to the word ordering, or the top 20 words. So we have things like film, movie, I want to say garbage, but it might be helpful. RB and LRB, maybe abbreviations. But we have a lot of things that refer to movies like story, characters, comedy, director, movies, action, and character again. Looking at this, if we look at this, this will be just the top words. So some of them could be very common across all the reviews. If we use what's called a term frequency inverse document frequency, we can see more weighted towards what's being said in reviews and not so much the global popularity of the words. So we still have story or like words like that, but we end up getting interesting words like goose, alien, feelings like amuses. I believe it says unrelated. Unreluctant.
Unelected.
Unelected, okay, thanks. I have a very...
You don't have it on your laptop, right?
No, I have notes on here. So it's a bit harder to read this. But yeah, we have a lot more of a description of maybe what the review's going on, what's inside the movie. So animals are like key subjects inside the movie. And it illustrates a lot more. This next slide actually shows the negative words. And what surprised me in this analysis, and I'm not quite sure how correct it was, but funny ends up being a very negative word. So I'm assuming they might use it in phrases like, it's funny how bad it is, or like something along those lines. But we have words like funny, bad, plot, hard, dark, dull, silly, worst, death, cold. On the opposite side, we have our positive words like love, humor, fun, entertaining, romantic, worth, sweet, pretty, fans, or fascinating. You have a question?
Just one comment about the funny term is that I imagine that, yeah, it could be, isn't it funny how? But it could also be something like a drama that's not supposed to be funny. But hey, this movie was too funny for what it was, or it was so bad it was funny.
Very accurate. I didn't think about that. So,
Listen, yeah, you can finish this slide because I have a question about this slide.
About this slide? Okay. Looking at these positive slides, it is really clear that we're looking at a movie review. It's almost as if they took it straight from the New York Times in their review post whenever they're trying to advertise for a movie, like funny, amusing, romantic, like those buzzwords that they use to describe a movie.
Okay. Can you describe what the x-axis is in this plot?
I believe that is the count for, let's see. So it's how much contribution to the sentiment it had. So the overall sentiment of a phrase or a sentence. Mostly a phrase because we are analyzing phrases. So this will be how much that sentiment attributed to that phrase.
Yeah, but it's not straightforward to me how that would be calculated, really. Like, let's say funny occurs 10 times in a positive review and 15 times in a negative review. Do we just say, I don't know, I mean, does anybody have any ideas?
In the tree that it had, it was like certain words contributed to sentiment, and sometimes, other times they wouldn't contribute to the sentiment. So I think funny would show up. I think funny would, if I'm remembering what I looked at correctly, I'm not sure if this is correct, but what I think it is sometimes funny would contribute to the sentiment, and sometimes funny wouldn't. So every time it did contribute to the sentiment, it would get added up.
Can you tell me how funny would contribute in some circumstances and wouldn't in others?
So there'd be like a tree of like all the phrases, and then it would identify in that tree which words are contributing to the sentiment or which phrases are contributing to the sentiment. And so sometimes phrases in that tree wouldn't contribute. I think that's great, but I'm not 100% sure.
One thing with funny is that comedies are supposed to be funny. So if it's funny, then it's funny.
You mentioned on the previous slide that you see the N apostrophe T there somewhere.
Oh, sorry. One more.
So maybe it's the modifier, so it isn't funny.
Yeah, I think it
So
really
you
has to do with
wouldn't
the
necessarily
negative.
count the is, but the N apostrophe T might be funny. I mean, what do I know?
No, so my comment to Matt about when funny would be a bad sentiment word, where it wouldn't be a positive sentiment word, things like a comedy, we expect them to be funny. So if you say this comedy was funny, that doesn't really say much. It doesn't add to the sentiment. Or if you say this drama is funny when it shouldn't be, that does add to a negative sentiment. So I think in that regard, funny wouldn't be a positive word.
Yeah, I totally understand it from a like understanding language point of view, but I don't understand it from a how is this being calculated exactly? Like the model doesn't have any idea about language, right? Like it doesn't understand the word funny and all the kind of context it can be used in, and how in some cases it's useful in some. Yeah, I would love to kind of hear from some other people on this.
Can we see the next slide?
Is there a? Oh.
Thank you. I don't know the answer, but I think there's probably a model that that this makes sense in the context of that model. So I think if you go to that URL at the top, the URL includes something that looks like LDA. So it's a model.
You may have to hold it down. Just wait till
Hello?
you see all the. There you go.
Good.
You're good.
I'm just quickly looking at the code for it right now. I think what the graph was trying to do was there's a score from 1 to 5 on how strong the emotion is, and then it's summing up how much those scores account for the positive and negative reviews. So there's 1,500 points worth of emotion in funny in the negative reviews. I think that's what the plot is trying to show. So if the word funny has a strength of, let's say, 2, and it shows up this many times, multiply that together, and that's how much it's contributing. I think that's what the plot is trying to show, if that makes sense.
Yeah, it makes sense, and there's a lot of theories. I don't understand the mathematical way of defining this.
I don't know exactly how it's calculated either, but the link up there links to LDA. So I'm assuming that if you follow that, then you'll find out.
So one last comment is, I think this should be, I'd be more interested to see what a standardized graph would look like, because if a certain word shows up in far more reviews, just based on the type of movie it is, then it would be skewed more. But that doesn't necessarily mean that it is a worse word per se.
Yeah, I think at that point, the word is just relative to the context it's used in, or the embedding it's in.
I kind of want to try an experiment. Dan, would you be able to explain how this LDA would be able to get to some number here? Would anybody be able to explain that? I'm not very familiar with LDA.
I don't know anything about this model. I haven't clicked on the link or read anything about it. The only point I want to make is I think that this plot doesn't make sense except in the context of a model that someone has built. So someone has some model that in the context of this model, there's an idea that they've called contribution to sentiment, and then they've made this plot. But to really understand the mathematical details of what this plot means, you have to understand what model they're talking about. So I don't know what they've done with their specific model, but I think if you want to understand this plot and the math behind it, you have to look into the model that they are using.
So the contribution here is just the sum of occurrences. Like looking at the code, it's just the sum of the occurrences of the word. No, I mean, like I'm just looking at the code. I'm telling you what's in the code.
So it's just, let's say whenever there's a slightly negative occurrence, whenever it's a 0 or a 1, count up every single time funny occurs there, that's a count. Whenever it's 3 or 4, that's a positive, count all of those up, and then just take the difference and say, okay, well, funny is contributing this many times to negative as opposed to this many times to positive. Something like that simple.
Yeah, it's pretty simple. So they filter out everything for a specific sentiment, so let's say negative, and they take these words, just summarize it by occurrences, and contribution is the sum of that, just for negative.
Again, I'm looking at the code. It looks like they're using a sentiment table called AFIN that assigns a number from -5 to +5 on how strong the emotion is. So I actually agree with what's being said. It's the sum of those, but it's not just one per number. Stronger words are given a stronger emotional ranking. So terrible, I guess, would be worth -3 versus horrible, which might only be -2, versus bad, which might only be -1.
Okay, so we need the context of the model, and then it's a sum. I think that is.
It's really summing positive. Shouldn't it be going for But these are only summing to positives. If it was like from a -5 to a +5, there'd be negative ranking, negative contributions as well.
I think red is
Am I
probably
right?
negative in this situation. Like, that's how I would interpret that.
Thank you.
Red is negative. We've got one more comment, and then we've spent way too long on this. But I haven't let you have anything to say.
Sorry if we're sorry.
So I think the simplest way I would do it is just run a TF, term frequency IDF, and then just the logistic regression. And then these would be the weights of the logistic regression. Like, so you would have the strongest predictor for a given category for a negative. So the weight would still be positive. The number would still be positive because it's associated with, say, the negative category.
Yep, that's similar to what Dan was saying about how you need a model, and then models kind of interpret how it is. Okay.
Okay. So, no. I honestly should have included the code. That way you guys could have seen what was happening behind it. If you do click on the link, you will find all the information on it. It's just a kernel that's open and they're discussing it. So some observations that we need to watch out for. We need to see stop words. So these are words like the, is, any common word. This will cause a change in the sentiment and could be an issue. A word like the might contain some kind of sentiment in this valuation, and it'll change the way that we'll end up evaluating sentiments. We have punctuation. So this is important because we can change the sentiment with that as well. So a sentence like, I will never not watch this movie again. It's very ambiguous, but it can change the sentiment as well. As far as I saw, word count and sentence like doesn't seem to affect sentiment too much, but I could be wrong with that. You guys might have other opinions on it. And then n-grams are pretty important in this, and we will need to be using them in order to break up and create more features. All right, so here were some of the approaches that we will cover and were covered in some of the kernels that I did read. We have LSTM, or a long short-term memory model. This is a recurrent neural network that classifies clusters or makes predictions about data like text or time series. So this would be a good choice for text. We have a convolution neural network. So this is used to classify elements or features and categories. Typically used on images, but in this case, it has been very popular in NLP, and there are a few ways of implementing it here. We have a CNN with a GRU, or a gated recurrent unit. This is an improvement on a standard recurrent neural network, and it uses two vectors to decide what information is passed to the output, and is designed to solve the vanishing gradient problem. In review, the vanishing gradient problem is an issue where the gradient doesn't change much and the weights aren't updated as intensely as they should be, and we don't get to an optimal weight in our neural network. There are bidirectional GRUs. This is two neural networks, one input in normal time and the other in reverse time. That way we get forward and backward information at each step. The glove word embedding, I believe it's global vector. I forgot the rest of the wording for that. But this captures word meaning in vector space, and it takes advantage of global count stats. We're using co-occurrence matrices to predict co-occurrence ratios. And then what we've already talked about, TF-IDF. So this is the term frequency within a document. In this case, our phrases. So how much does it show up in a phrase? If it shows up a lot, it's very important for that document or that phrase. As compared to the inverse document frequency, where we see, okay, well, it also shows up a lot inside of the rest of the documents. So maybe it's not that important. Maybe we should give it a lower weight if it shows up too much in other documents, as well as just this document here.
Actually, yeah, I'm going to make a comment. I took them all down. Okay, this is actually a great page to talk about, because like it's all the models right in front of me. CNNs for text. You're right. They were originally kind of like, they got famous in images, but they are used in text like quite often. I use one in text at work. Long short-term memory also solves the vanishing gradient problem.
Oh yeah, no, it's I did have it in my information as being a version of the GRU. Like it can work.
Yeah,
as another version of that.
A GRU is kind of like a simplistic LSTM in some ways. Yeah, and the glove word embeddings are essentially inputs to the LSTMs and GRUs.
Yeah, yeah. Some of these are things that you would do as pre-processing before you send it into the other networks, and yeah, I kind of glazed over that a little bit.
That's okay. No, you did a good job. I just wanted to clear up a couple of things.
Okay, so this is one of our first actual pieces of code. I will note that I am not going to talk too much about logistic regression or 1V rest, because the last presentation we did cover that, and in the slides I think it's pretty in depth. So I didn't want to bore you guys with a repetition of that, and I decided to focus mostly on neural networks in this one. But I will go over the code a little bit. We do have a TF-IDF vectorizer that will give it 1 to 2 n-grams, and then we tokenize it here. We take the full text and we basically merge it together in order to create our vectorizer fit, and then we train and transform our train and test phrases, set up our sentiment, and then we do all of our testing. So this is a lot of stuff. I took a broad picture of the notebook or the kernel. If you look at the bottom.
Can I interrupt you? Just to go back for a moment. This is just sort of, I think this is just an interesting little thing to pull out here. This is not necessarily totally clean practice here. I guess it's worth thinking about. I believe what we're doing here is we're actually taking our test set and our training set in order to compute these TF-IDF values. And when in these normally in these modeling situations, you might be creating a certain amount of leakage when you're doing that. And so, especially also, like, there's going to be like a validation split here eventually as well. So there'll eventually be 3 piles of data, and you might want to firewall off some of them more. So just like a detail to pay attention to.
In this case, would you use that cross-validation set in place of the test set?
I'm not sure exactly what I would do. I'm just flagging up that this is the kind of thing, like when you dump all of this data into one big pile and compute summary statistics across it, and then loop that back into your features, you're starting to flirt with fire.
It's a great point. I'm just going to point to the lines that you're talking about. So we're fitting the TF-IDF vectorizer here. This should probably be fit only on a training set so that the test set and the validation sets do not have a chance to kind of enter into the mix. And then you can fit it here, and then you can transform them. You can transform the test set with this fit vectorizer. This is what you're getting at?
Yeah, and like I could be sold on the idea that this is okay, but like I have my doubts, and so I just wanted to like.
If you want to do well
this is a thing that a team should have a big debate about. Basically, is what I'm saying.
If you want to do well in a Kaggle competition, you would definitely just want to use all of your information, all of your data. But if you're building something for production and you don't necessarily know what sentence is going to be coming in, so you can't really know how those words are going to affect like the rest of your distribution. To get a good validation score, you would not want to fit on your validation set. So I guess I can see it having an advantage if you're competing, but.
Sorry, in Kaggle, the private leaderboard is usually held out data that you never get to see, right? So you
get to see it, you just don't know the.
yeah, you don't see the labels. The labels are hidden, right?
But you know the text.
But if you make a mistake and fit on a data leak, or fit on a leak like this, then you'll get a model that won't generalize, right? So you won't do well on the private leaderboard.
So essentially the information in the TF-IDF is how important or how often do these words occur. And that, if you're never going to have any other text coming into your data set, you want that to be as representative as possible. So you want to use all of the data that you have, including data that doesn't have labels. And that should give you a better representation of how important each word is or not. And so you would want to use everything.
Okay, but then it sounds like that should work in production too, right? If it is good at predicting new data, then you're okay, both in Kaggle and in production.
So I'm convinced now that this is okay, but now I know what I think. I think I'm confident what the distinction is here, and that is like when we do things in real life, we're using our test set to try and predict what our real world performance is going to be. And if we allow this kind of information in our held out test set to leak in, we're going to overestimate our real world performance because we're going to do a little bit better than we did against data we've never seen before. But in Kaggle, we don't care about our real world performance. We want to maximize our test set performance. And so we should embrace the leakage in this case. But the scores in this competition would probably be slightly higher than if you actually did this in practice, because they're probably all biasing.
Yeah, actually, so Dan, you convinced me you probably should do it in practice because it does give you a slightly better representation, but you will be overestimating your errors in this case. Okay.
I kind of wanted to ask a question about like if you are doing something that like this, but you don't want to like overgeneralize on that test set, you actually want to like do a cross-validation and see how realistically accurate you are. Would you split out the cross-validation set from the train set before you do the TF-IDF vectorizer?
Yes.
Thank you.
Okay, at the end of all of this, we end up putting a logistic regression into a 1V rest classifier and then training all of it.
Sorry, Alexa, is your mic muted? We get a little bit of feedback. Oh, I guess it's okay, thanks.
So looking at the accuracy off of a cross-validation on our validation test set, we end up getting about a 56.55% accuracy. So this Not very impressive. Could be a lot better, very close to 50%. Then comes SVMs. So we use the same setup here, but then just switch it to an SVM. We end up actually having worse accuracy at 56.51%. But here's the code. We basically just throw everything we already had. We create a linear SVC, which is Python's way of saying support vector machine. And then we throw it into our cross-validation with the same parameters that we had before. So I wanted to take a quick stop here because I found it interesting seeing TF-ID vectorizer because I saw it in the last presentation we had, and it had completely different parameters being used. So I wanted to quickly look at these parameters. So we have our n-gram set, which is set 1 to 2 n-gram creation. And so that just creates different features like, say if we had a phrase like, I like dogs a lot, we now have a bunch of different n-grams of I like dogs a lot, and then we have our individual n-grams of each word. The tokenizer helps to kind of tune the string and put it into a vector. It will convert these into numbers. Moving on, we have our LSTM model, and all this stuff up here is going to be used later on for the rest of our model tests. I didn't realize it while I was creating the slides, so it's a little bit messy in this one. I would have separated the slides, but here we go into a little bit of the information. So we're going to set our max amount of features to the number of unique words in our set, max words to the max review length. We're going to have batch sizes of 128 phrases, and we're going to do about 3 epochs or 3 different runs through the neural network. I did not end up looking up what that was, but then we have our tokenizer that sets up, basically converts it to numbers. We do it on all of our data separately this time, so xtrain, xvalidate, xtest. We then add padding so that we can preserve the data and don't lose anything while we're doing any maybe convolution or something like that. We move down, we set up our model, so we're setting up sequential so we can start adding layers in. After we set up that, we do word embedding, which is going to create a dense vector that'll tell us where this word's occurring and what it's occurring around. And then we move on to our LSTM, and then we know we have 64 nodes with a dropout rate of about 40%. This means we're trying to prevent overfitting by dropping out specific nodes in a subset, so in this case a 40% subset for just this layer. And then the next layer we have 32 nodes with a dropout of 50%. And we move on to a dense layer, which is a layer that takes in n inputs and puts out n outputs. It's just very dense with a softmax that as an activation function. So in this case, softmax basically acts as a sigmoid function, but it will have more than just zeros and ones. It will give you anything between 0 and 1, and then all of the information being fed out has to add up to 1. So it's a good way to edit your data while it's coming through the neural network. And then we just compile all this together with our categorical cross entropy, and then we use an optimizer in order to make sure that our gradient is in the proper way. So here is the epoch breakdown. We have about 124,848 samples, and we're validating on 31,212 samples. So our first accuracy measure on the validation set is 64%, and our neural network is doing all right at about 57%, and it gets better over time. So we start with it being 57% accurate on the training set. And then we move on to 65% and 67%. If we look at the validation set, we end up gaining about 1% each time. So this is fairly good, but I think we can do a little bit better.
Out of curiosity, why just 3 epochs? Because judging from the numbers you got out of there, it doesn't look like it's converged yet.
Yeah, I was wondering that too. I think it was because they were just trying to show an example, and they want to make it very easy to look at, and not necessarily go to the full optimal neural network. But okay, that was just my assumption.
Fair enough.
So moving on to a convolutional neural network, we do the same setup with sequential. We get our word embeddings. We set up a dropout rate for that, and then we get our one-dimensional convolution layer. This has 64 nodes, and then there's the kernel size. So kernel size ends up being how many features you will put in this convolution layer. So we have 3 features. Padding is the same, so we're maintaining our padding size, and then we're using rectified linear units. So this one means that anything below 0 will be converted to 0, and anything above will be preserved. So that means if we have anything that's going below 0, we don't care. We're like, oh, well, it might as well this node might as well be off. And anything above, we're like, okay, we want to see how on this node is.
Can I ask a question? So this is something I know is kind of a bit of a gap for me. Line 2, this magical embedding. Can anyone give me the TLDR on that?
I can do that.
Can you?
Sure, I can do that. It's just essentially, it comes up all the time when you're trying to embed some sort of, so in this case, it's a word, and we're saying each word we want to represent by a vector. This is what this layer is doing. So you're saying max features, is that how many, can you go back a slide?
That was unique words. Yeah.
Okay, so number of unique words, that's how many different sort of, it's going to take as input like a 0, 1, 2, 3, like an integer, and it's going to expect to have the number of integers that it could be is the max features. And then it's going to output a 100-dimensional vector. So for each number, it's going to get a unique 100-dimensional vector. You can imagine this is just like a big matrix.
Is it just a linear layer then?
It's just embedding that. It's just saying if I see a 1, then I'm going to represent it by this vector. And then that's trainable. So you can go all the way back up there. So in the previous slide, you mentioned that embeddings is like taking the surroundings. That's typically how embeddings are trained, like in a unsupervised way. That's how embeddings are trained. In this case, it's just trying to figure out which sequence of numbers will best like represent this word.
Yeah, it's a learning parameter, right?
It doesn't look at anything around it. Really, it's just yeah. Did that explain it? You look confused. It's just a mapping. It's just a mapping, Alexi.
So so I understand what an embedding is, and in my experience, that has always been something that you would usually do by hand. Like you would pick up your data and embed it into whatever dimensions you want. But here it looks like it's a layer that does that. Is that correct?
I must have explained myself very poorly. Sequential model. This is the very beginning. The input to a sequential model is just going to be a list of integers that is going to represent your sentence. So if you have a sentence like "I like dogs a lot," maybe "I" you'll give every single time you see the word "I," you're going to give that the number 10. Every single time you see "like," you're going to give that the number 11 and 11, 12, 13. So your sentence as input to the model is just going to be 10, 11, 12, 13, 14, 15. But the neural network doesn't know how to use these numbers. The neural network wants vectors at the beginning of each thing. And so that's what this layer does. This is just saying, okay, well, I have an input of numbers, but now I want an input of vectors. And you can have a pre-trained embedding layer. If you want to use Glove or something, you can import all of these weights. And so this layer wouldn't even be trainable if you wanted. You could just say, I only want to use Glove vectors. And Alexa's not even listening to me. I'm more than happy to talk about this more over lunch.
So if I've understood correctly, then what's happening here is basically the embedding that's actually generated here is being trained through the back propagation of the network. Is that correct?
It is.
Okay.
So really the start of the network is the CNN layer, is the conv layer.
I wanted to ask if is that embedding, that like mapping, similar to like when we talked about the PointNet paper, how those were being transformed into like different dimensional vectors, like how you take like those numbers representing, words, they get transformed into like a 100-dimensional vector. Is that similar to that? Like how you transform features into a different shape?
Sorry, so as the expert on the PointNet paper, because I was the one who kind of led that discussion. So yes, except this is where I like struggling with this, is like when we do these feed-forward neural networks, like we're always transforming inputs into new vector spaces. Like that's what you do at each layer. And so like in the PointNet, we have like these these CNN type style layers, and then we'd have this, eventually we have a feature vector that represented the inputs. And like if you have a normal feed forward neural network with dense layers, like the output from the first layer is like an embedding. Like we took the input data and we put it into this new differently dimensional space. And we did it again and again. And so that's why I'm like struggling to differentiate like what is really going on here. And indeed, like we normally either take embeddings that somebody else created or we explicitly create an embedding. But in this case, it's like somehow a module. And like, so why is this different from like, I mean, even when you take an image and you run it through a pre-trained like CNN classifier from ImageNet and you take the final layer of features or whatever, that's an embedding, right? Like we took images and put it into this space.
Okay, I have an idea. I'm not sure if I fully understood your question, but we want a very, very hard constraint on this in that every single word has to be independent from each other. So they shouldn't be going through at the same model at all. There should be nothing like the word like and the word I should be initialized randomly with some random numbers, and they should be trained completely separately from each other. And so each one has to start with a vector, and you have to assign that vector at some point. And so this is just the layer that stores that mapping. Like has the vector, I don't know, random assortment of 100 numbers.
Okay, so this is a matrix that is max features by 100.
Exactly.
And we're just doing lookups in that matrix,
Exactly.
and we're going to use backprop to train the values in there.
Exactly.
Maybe.
Even though versus...
I think we're diminishing the value that this layer is adding, and I disagree. The network starts with that layer, not after that layer. And it's more than just a mapping. It's not just a convenience or something. There's some serious dimensionality reduction going on here, right? We're targeting a huge number of features. I lost track, 5,000, 10,000 or something, and knocking it down to 100 dimensions. So, like word to vec and how the vectors that you get out of that have almost semantic kind of interpretations. So we're not using a pre-trained embedding layer here. We're going to learn our own. But presumably, the way that embedding works and that dimensionality reduction works and where those vectors live in that space, you can do that in different ways, and there's a way that's going to work for the subsequent processing and analysis and identification of sentiment. So it's basically, so we're not doing word to vec, which specifically looks at co-adjacent type things. Excuse me. This is going to learn that, but it's going to learn it in the context of the problem we're trying to solve. So there's something significant going on there in that mapping from the big feature space to this lower dimensional vector space. Maybe I'm saying the same thing everybody else has already said.
Yeah. No, Bruce said it in much better way than I did. It is doing something.
I actually think that we're just looking at some extract from the code, so we don't see what's happening between because I guess this is keras, right? So if you look at the definition of the keras embedding layer, it says that it can be used for both actually training from scratch and actually using the word2vec or glove or anything like that. So I'm not 100% sure if this is actually training from scratch. It may so it doesn't provide like the input as a glove or something like that.
No.
Well,
and even if you provide input from glove, those are just your initial weights for each.
Yeah, well, you can randomly initialize them and you will get that behavior in the end. But like, why wouldn't they use pre-trained embedding? And actually, I would argue that maybe pre-trained neural network would work as well. Is it this year a competition, or was it like old competition?
It was within the last month or so.
So in the last year, that like a big advance in the NLP was actually using pre-trained neural network. So I would argue that I would try not only pre-trained embedding, I would try actually the whole model pre-trained on quite a big,
So later on, they will, some of the samples, they end up going into glove embedding as the first embedding they will put into the neural network. And we will see them doing that, but this is just without any pre-trained embedding because they were just trying to show a CNN as it was learning.
This is directly related to the last comment, so I'll jump in here. I actually just finished reading the book by Francois Chalet, who wrote Keras. Pretty great book, actually. I recommend it. Easy to read, understandable, and obviously oriented toward Keras. Anyway, he made the comment in there about pre-trained networks, of embedding networks like GloVe or Word2Vec. And unlike in the world of image processing, where it's just like the first thing you think of is using a pre-trained ImageNet type CNN to solve your problem, it seems to be not so much the case when it comes to NLP and pre-trained embeddings. And his view was that typically you will want to learn the embedding rather than start with a pre-trained one. And I'm sort of extrapolating from what he said. I think the reason is you've got a particular domain that you're dealing with here. The pre-trained embeddings are on all of Wikipedia or something like that, and they're attempting to capture in English, general English discourse. This is kind of where words would get embedded. But we're not dealing with such a broad, all of English literature here. We're dealing with movie reviews, which is a much more restrictive kind of domain. So learning the embedding it seems to me it's a more typical way to go than to use a pre-trained.
Yeah, in practice, I never start with pre-trained embeddings. Just to...
3 words, he said.
So moving on later in that line, we have the stride count, which is how far it'll move across, like convolution will move across the vector, the matrix. It's set to 1, so we'll just be moving 1 unit at a time. The next line, we're adding our global max pooling. So we will be going through this matrix and looking for the maximum sizes and trying to move them into a new matrix space. After that, we feed it into another dense layer. We do more dropout, and then we add another dense layer. So here's how that broke down. We have the same amount of sample and test validations. It started off at a 65% accuracy, and the test data was the training data was about 59%. We moved up to 66, and then it got better at the test data at 67%. And then here, it started pulling away a little bit. So I imagine if we were to train it a bit more, we might run into some overfitting issues, where it'll start being really good at the training data set, but very inconsistent or not as accurate with stuff it hasn't seen before. Then we have the CNN with the GRU model. Same stuff as before. We have the sequential embedding. We do our one-dimensional convolution layer. We do our max pooling. We have a new dropout there, and then GRU's added. So this is 128 nodes. More dropout. We actually flatten it before we move it to another dense layer, and we repeat this again, dense dropout. So overall, same sample, same validate. We start out at about 65% accuracy, and the training data is about 58%. We keep moving up. It's kind of matching itself, so we aren't really worried about overfitting, and we get to a new higher percentage of 67% as the third iteration through this neural network in its accuracy. Again, bidirectional GRU. This one changes by adding spatial dropout for one-dimensional, and then we get the bidirectional GRU with 128. So this one, same sample size, same validate size. The accuracy is at 64% in the beginning, basically almost 60% for our training data. And then it keeps moving up. We end up at 67.13. So it's not too bad with overfitting. We might see a bit of issues if it keeps going up like this. But now we're starting to get to a much higher accuracy rate. So now we're doing the part with actual GloVe embedding. Here is where we're embedding the actual code. So it's this embedding matrix, and that code's right here. I will not get into that one. I didn't really review this code, so that's to your discretion. Please take a look at it. You'll see how they did the training for the GloVe vector embedding and then how they implemented with this. But what I know is that they did import it from here, and then they did the same spatial dropout, 2 bidirectional GRU layers, and then they continue with dropout and a dense layer. So this one actually got all the way up to a 67.96% accuracy. And it was better on the validation set than it was on this training set. So at this point, I wanted to just quickly go over what a CNN is. So in this example, we'll be using a picture as an image input. And we're looking at some convolution size. So we'll move across in this size of convolution over all the pixels in this matrix. And we'll go through and we'll start putting them into a new convolution layer. This has the tendency to sometimes miss data if you haven't padded the data, because you might have an uneven amount, like it might be a 3x3 matrix that's being convoluted, and then it will be an even number, like a 10x10 matrix that you're going through. So the convolution is basically the dot product across this matrix with the information that's inside of the original image layer. We move into this convolution layer, and then in this case, we're doing 2 layers of convolution and then 2 layers of pooling. So pooling is where, like before, you check for either a max or some kind of value you're looking for. So you could have like average pooling, min. I don't know if you'd need min pooling, but average or maybe max pooling, where you're going to find like the average of a whole matrix that you're looking through, or maybe it's just the max out of that matrix that you're looking through. Basically, you go through this, you hit a flattening step, and then you go into some kind of classification step. So at this point, you'll be like, okay, so we have a car. We're going to classify it as some percentage likelihood that this is a car. What happens here is you will take that percentage likelihood and minus it from the actual value. So if it was 100% a car in the training set, then you'll say if it's 25% a car, we were off by like 75%, and we'll use that in a weight calculation in order to retrain the data as we go back into it. I just added this to give a little bit of a look at a gated recurrent unit. All I really know about the gated recurrent unit is it is used to help stop the vanishing gradient problem and move data along. I wanted at this point to start a discussion. So why are CNNs popular in NLP? Because it's a question I had and I didn't find much information in my research.
I feel like I've talked way too much already, but this seems kind of down my alley. CNNs are good in some NLP tasks. They're not good in all tasks. CNNs essentially throw away a lot of the positional data. If it really matters that you're saying a sentence, like if you're really trying to translate a sentence or something like that, CNNs lose a lot of that ability. So CNNs are never used for translation, for instance. CNNs essentially just grab everything and throw it, because you usually do a global pooling after all of your CNN layers. So they're just looking for occurrences of a word. Or if you do a character-based CNN, they're just looking for a sequence of letters that are indicative of a certain output. So I'd say that CNNs are very popular because in a lot of cases, position doesn't actually matter, and in a lot of easy classification tasks, you're really just looking for certain words or certain sequences of characters, and that is exactly the signal that CNNs are great at picking up on. Please, and can you go back to the CNN page?
I think I agree with everything Matt just said, but also it's RNNs are the other popular architecture thing to use, but they have a lot of parameters and they're a little harder to train, and CNNs are just a lot faster to train and to run at different times. So I think there's a lot of interest in CNNs for that reason as well, just a performance issue.
So I have a question for Matt, and would you be able to get a better sense of the structural arrangement of phrases if you would use a longer convolutional filter? I saw that those models, they were using just a 3-long kernel. So I imagine that on the first pass, it's only able to look at patterns of 3 contiguous words. If you would increase those filters, maybe you would be able to catch larger phrases?
Yeah, that's a great point. Actually, what I do in practice is I think sometimes 3 characters, so I'm to speak in the context of characters because that's what I deal with. 3 characters is sometimes important. Sometimes the signal is just captured in 3 letters, like 3 letters is all that matter. Sometimes it's 4, sometimes it's 5, sometimes it's 6. So you can actually add a whole bunch of different kernels here and have those all kind of concatenate together after the global max pooling. And so you can actually capture a lot of different window sizes at the same time. So if something is 7, if something needs like 10 characters for like 2 words together, that is something that it can now capture. Whereas it's not capable of capturing that with just this 3. So that's a big weakness here. I would be curious how well, because I'm a big CNN fan for NLP, obviously. And this seems like maybe a model that is not really done that well.
And would there be an actual cost if you just made that kernel bigger? Like, if there's no information, probably those neurons would be knocked down by some regularization term or something. So, like, if I was going to tackle this problem, I would just throw like a 10 long one-dimensional kernel and see what happens. Wouldn't that be a sensitive approach?
Yeah, but you could do, I think if you only have a 10-dimensional, or a window size, are you saying window size of 10? Yeah. Then you might be missing out some information that you only need a couple of characters to get, or, characters to get.
Those filters would still be there, right? Like if there's information that you only need 2, wouldn't there be a filter that is like basically zeros and 2 characters? Would that make sense?
Yeah, but that's much more, in theory, it would happen like that, but I think that would be much more difficult to arrive at during training. And so there's not really a cost of just having 3, like you can have 3, 4, 5, 6, 7, 8, 9, 10. You can have 100 of all of those different kernels, and that's what I'm doing. If there's anybody that has a different opinion.
This is an extremely low capacity network, right? So I mean, we're essentially proposing adding capacity to it. And so like, and it didn't overfit much really, right? So that's not, so like, yeah, you could make this kernel wider and I think that wouldn't be wrong, but you might want to add more layers, right? And if you add a second layer with kernel size 3, now we start to look into things like a receptive field, or at least that's what we call it in images. I don't know what you call it in these sequences, but what is the receptive field here? We might dilate these convolutions, things you guys could look up if you wanted to know more about them.
Actually, a point of miscommunication on my part, actually, I would be adding them at the exact same layer. So I would
I know, but you might want to go deeper. This is like a 1-layer model.
Yes, good point. Yeah, you could go deeper. And then you can start getting context, I guess, if you didn't do the global max pooling and you did kind of like shorter poolings. That's like the input to the GRU. That doesn't do the global max pooling. It uses that tries to get the positional information. One more point on CNNs, and we can talk more about it at drinks if people are still interested. They're super fast to train. So that's one huge advantage of why people use CNNs as opposed to LSTMs. Like many factors of times faster to train a CNN than an LSTM.
And the reason is parallelization. That basically every step of these recurrent neural networks cannot be computed until you've computed the step before. But with the CNNs, you can just batch up these whole vectors.
All right, with that said, that's all the stuff I was covering. One thing I'd like to say is this is only my second Kaggle Meetup, so please think about presenting. I've learned a lot more than I would have learned coming to a few of these just because I had to do a lot of the research myself and I was able to understand the context of discussions a lot better because it was something that I had a lot of background knowledge in. So I suggest any new members or anyone who's interested, do see about making a presentation. It's a very good way to really solidify some ideas or at least get better understanding of concepts. But with that said, thanks for having me.
Does anybody have? We have time for questions. If anybody has questions for Derek specifically, maybe Derek, what were you doing before you decided to come here? Did you cover that?
Just a quick question. If anybody tried ensembling, just taking like SVMs, taking linear regression and I don't know, CNNs and putting them all together?
I didn't see anything like that. No, I didn't see anyone trying to mix them all together.
Thanks.
I realize you covered where you came from in your slides, so I won't redo that question. Any other questions?
I mean, maybe just like an observation, like, so these models that we were just looking at, I mean, any single one of them was, you know, kind of unimpressive. They'd largely been like simplified in order to be a nice demonstration, right? Like that CNN we just looked at and so on. And yet, like, I mean, what was the second place leaderboard score and what were the performances of these models, right?
Yeah, they got very close.
Yeah, so that must be interesting then. And what must separate number 2 from number 22 and number 202 must be like some of this ensembling or something, like when you need to start squeezing out those small percentages. I like this, like that's my observation. I don't know what the actual situation was, but there's a small gap, really.
Yeah. Honestly, from 10 to 2, it was about 2%, or maybe some change.
A couple of comments from the live stream. Yes, people are actually on the live stream. We got a pretty healthy turnout tonight. Robin's there. He's often got a lot of things to say. So when I was pooping all over pre-trained embeddings, he did point out that if you don't have a lot of data, it's good to start with a pre-trained embedding and then work from there. That's totally fair enough. He also comments, as we're talking about the window size for a CNN, in my opinion, a 10 window should still catch smaller sizes, but this is only my intuition. So that's what Robin said. I'll kind of push back on that a bit. It seems to me like a kernel size of 3 is kind of like looking at trigrams, maybe, is sort of what it's doing. And my understanding, and I'm not an NLP guy, but that going beyond trigrams, it doesn't add that much, and it starts to get confusing. Like most of the intent of what's going on is captured by the 3 groups of 3 words rather than 5 or 10 or something like that. If it's important to capture high-level features that extend, like if you're doing translation from one language to another and you need to understand the structure of an entire sentence, then I think you would stack layers and capture those higher level features, or you use an attention model or something that specifically gives you a way to look across the whole sentence. But I think in terms of a kernel size for the CNN, 3 seems like, to me, not knowing anything about it, seems about right. Yeah, Pao?
Yeah, so to me, 3 also seems all right when you have a deeper network. And I think that's more or less the tendency. So I think that the field started with larger kernels, but as we went deep, we realized that, well, you actually can use smaller kernels because since you're passing one convolution after the other, after the other, after the other, every time that you pass a convolution, it's like you're blurring the data. You're doing like a Gaussian of the data. So at the end, parts that are further away, they get pulled together in the equation just because you had so many layers. So yeah, if they had more layers, I wouldn't have complained, but with just one layer, yeah, I would have used a larger one.
Yeah, and that history that you described of starting with larger kernels and going to smaller ones, I think you're talking about image classification networks, maybe in particular. And I'm guessing that maybe the NLP world has learned a little bit from that, and just 3 is working really well for images these days. In the earlier days, they started with 11 and 7, but 3 turned out to be really good for the sort of reasons that you're saying. It's better to stack the layers and get the information collected up that way rather than trying to do a big kernel. And I guess they just adopted that for NLP as well.